So for our second short answer, FRQ, we have the same scenario, same bar, same mass, same peg, same setup. But they say here with the mass in slot A, this bar mass system is motionless. So we know that our forces are balanced and our torques are balanced. So part A asks us to find the mass of the cylinder. So we don't know how far the holes are spaced, but since the holes are evenly spaced, we can use one hole as a standard unit of measurement, just like we've used similar things in the past. So we know that since the bar is motionless, the sum of the torques is 0. So the two torques acting on this bar, causing it to rotate or not rotate around point C, are, first of all, the mass itself that's hanging at A. So remember, torque is equal to the force times the distance from the axis. Now, we know that in this case, everything's going to act perpendicular, so we can kind of not neglect the sine theta term, but we know that all of the thetas are 90 degrees, and so that all of the sines will be 1. So the weight of the mass itself is capital mg, and then its distance is 2 holes, because it's 2 holes from the pivot point, all right? Now, the bar itself has mass little m, and maybe you even say over here, big M is the cylinder, little m is the bar. You kind of want to make sure that they know what you're talking about. So the weight of the bar here times mg, and then it's 1 hole away. And as you can see, the actual unit of hole or hole distance cancels out. Gravity cancels out, and we have the mass of the bar is twice the mass of that cylinder, which does make sense if the cylinder has to be twice as far out for it to apply the same torque. Maybe you got that sort of intuitively, but it doesn't take much effort to show your work there. So we get 1 point for the answer itself, and then 1 point for applying this net torque to be equal to 0. So in part B, now we're putting these bars on a horizontal table, and now the pegs are vertical, so you kind of got to flip your brain 90 degrees there. These are 2 uniform bars of the same dimensions. They're constructed from the same material. One bar has 5 evenly spaced holes, and the second bar only has 2 holes. In these cases, the bars are slid over vertical pegs and rest on a horizontal surface, where friction between the bar and the surface is negligible. The 2 bars are each pulled by horizontal forces of equal magnitude F from their right end as shown. The bars' resulting accelerations are recorded. Is the magnitude of the initial angular acceleration of the bar in case 1 larger than, smaller than, or equal to the magnitude of the initial angular acceleration of the bar in case 2? So each bar is going to experience the same torque, okay? It's the same force, it's the same distance from the pivot point. So their torques are going to be equal. Now, we know that torque is equal to I alpha. So I'm going to say the moment of inertia in case 1 times the alpha in case 1 is equal to the moment of inertia in case 2 times the acceleration in case 2. This is what we want to compare. So we're going to need to compare the moments of inertia for the bars themselves. Now, we can't calculate the moment of inertia of these bars because, especially with the holes cut out, we don't have a formula for that. But we know that moment of inertia is always proportional to the mass of whatever we're dealing with. So if we've got 2 things and they're shaped the same way and one has more mass, then it's going to have a higher moment of inertia. So since we know these bars are made of the same material, we know that the mass of bar 2 is going to be greater than the mass of bar 1 because it doesn't have the holes taken out of it. Okay, so the moment of inertia then for bar 2 is going to be bigger than the moment of inertia for bar 1. So erasing this, if the moment of inertia for bar 2 is larger, then its alpha is going to be smaller. The moment of inertia for bar 1 is lower, the acceleration is going to be higher. So the answer here is that alpha is higher in case 1. All right, and we get 1 point for that part of the problem. 1 point for saying that the torques are equal for each bar by realizing that F times R sine theta is equal in both cases. You get a problem there. You get a point there. You get a point for realizing that moment of inertia is less than in case 1. Then you get a point for actually saying that tau is equal to I alpha, and then 1 point for the clear and coherent paragraph. So there's 1, 2, 3, 4, 5 points for part B. So in part C and D, we have another collision in the same sort of vein we had in the last problem. In case 3, we have an object landing on the bar and colliding with it and sticking to it, and the bar begins to rotate clockwise. In case 4, we have a more elastic collision here, where that ball hits the bar, causes it to rotate, but in case 4, that ball's not going to stick. It's going to bounce back up in the reverse direction. So part C and D say, is the resulting angular momentum of the bar greater in case 3, case 4, or the same in both? And then part D is our explanation. So let's tackle those together. The answer there is that the final angular momentum in case 4 is going to be larger in case 4. So that is the answer for C. Now D is the Y part. So if you look at this problem and if you look at them together, it's probably easiest. Before the collision, neither bar has any angular momentum, and each of the balls have equal angular momentum. All right, each of the balls have equal angular momentum with respect to the pivot point there, the MVR. Okay. But what happens in the collisions is very different. What happens in case 3 is that the final momentum of the clay ball is also in the clockwise direction, but the final momentum of the ball in case 4 is in the counterclockwise direction because it reverses its motion. So in order for the final momentum of that bouncing off ball to actually have some in the other direction, it needs to impart even more of that initial momentum to the bar. So again, each object has an equal angular momentum before the collision, and they're clockwise, right? In case 3, the final momentum of that object is still clockwise, but in case 4, it's counterclockwise. So it had to not only give that object enough to start going, but also enough to kick it back. So that's the answers for C and D. For part C, you get 1 point for identifying that the momentum will be greater in case 1. For part D, you get 1 point for using conservation of momentum, and then 1 point for saying that delta L for case 4 was greater, okay, because of the object. Delta L for case 4 of the object was greater, so that delta L for the bar must also be greater. So 3 points total for C and D.